Now the amplifier comes into play. Let's consider the amplifier in conjunction with the circuit on the left. Does this circuit function as a high-pass or low-pass filter? This circuit serves as a high-pass filter since a capacitor is positioned at the input path. This capacitor is also referred to as an AC coupling capacitor or a DC block. It allows high-frequency signals to pass through while blocking low-frequency signals from entering the amplifier input. Moving on to the circuit on the right, a capacitor shunt to ground is added at the amplifier input. What type of filter does this circuit represent? This circuit functions as a low-pass filter since high-frequency signals tend to go to ground more easily at the input. The amplifier on the left features a capacitor in series in the output path, which is an AC coupling capacitor. What type of filter does this circuit represent? This circuit serves as a high-pass filter. In the circuit on the right, a capacitor is shunted to ground at the amplifier output. What type of filter does this circuit represent? This circuit functions as a low-pass filter since high-frequency signals at the output tends to go to ground rather than reaching the load. If we insert a series LC on the input path of the circuit on the left, what type of filter does it become? This configuration functions as a bandpass filter since the input path acts as a short circuit at its resonant frequency. If we add a series LC to the output path of the circuit on the right, what type of filter does it become? This configuration functions as a bandpass filter since the output path acts as a short circuit at its resonant frequency. Suppose we add a series LC to the amplifier's input, as well as shunt it to ground. What type of filter does this circuit represent? This circuit functions as a band reject filter, since the path acts as a short to ground at its resonant frequency. What type of filter does the circuit on the right represent? This circuit functions as a band reject filter, since this path in the output behaves like a short circuit to ground at its resonant frequency. Suppose we use a parallel LC circuit at the amplifier input, but in series with the input signal path. What type of filter does it represent? This circuit serves as a band reject filter since this path acts as an open circuit at its resonant frequency, preventing signals of that frequency from passing through it. So, what type of filter does the circuit on the right represent? The circuit functions as a band reject filter since the output path acts as an open circuit at its resonant frequency. Suppose we use a parallel LC circuit at the amplifier input, but shunt it to ground. What type of filter does it become? This circuit functions as a band pass filter since the path at the input acts as an open circuit at its resonant frequency, allowing signals of that frequency to pass through to the amplifier completely. Lower frequency signals will flow through the inductor to ground, while higher frequency signals will travel through the capacitor to ground. Thus, it functions as a bandpass filter. As for the circuit on the right, what type of filter does it become? Simple. It is a bandpass filter. Now, suppose we have an amplifier and place a capacitor on the feedback path. What type of filter does this circuit represent? If you can't tell it quickly, pause for a moment and think about it. The answer is that this circuit functions as a low-pass filter. You might wonder why the circuit with an amplifier and a capacitor on the feedback path functions as a low-pass filter rather than a high-pass filter. Although low-frequency signals cannot pass through this capacitor easily, high-frequency signals can. However, we need to consider that the amplifier now features a negative feedback structure. This means that a certain percentage of the output signal is fed back to the input to reduce its error. The negative feedback amplifier aims to minimize the input error. In the case of this circuit, the positive endpoint is grounded, so the return signal will reach the near zero potential endpoint, also known as the virtual ground. Alternatively, we can say that the error between the return signal and the input signal should be small, meaning that the input signal will be cancelled out by the feedback signal to achieve this objective. Thus, inserting a capacitor in the return path implies that the higher frequency signal is more likely to be returned and then eliminated at the input. Therefore, this circuit functions as a low-pass filter since high-frequency signals are more easily eliminated. Now let's focus on the circuit on the right. Just think about it. It's really quite simple. This circuit is straightforward. It functions as a high-pass filter. This is because low-frequency signals are more likely to come back from the output to be cancelled out at the input. Therefore, high-frequency signals will be more prevalent in the output. Suppose we insert a series LC circuit on the feedback path. What type of filter does this circuit represent? This circuit functions as a band reject filter since the return path acts as a short circuit at its resonant frequency, enabling the signal with a frequency close to F0 to return and be eliminated. Signals far from the resonance frequency are less likely to come back and are more likely to be amplified. Now let's focus on the circuit on the right with a parallel LC circuit on the feedback path. What type of filter does this circuit represent? This circuit functions as a bandpass filter since the return path behaves as an open circuit at its resonant frequency, making it more difficult for signals near F0 to be cancelled out by the amplifier at the input. As a result, this circuit is a bandpass filter. Okay, these are our 28 common and simple filters. And of course, when we come across other circuits, we can attempt to apply similar concepts to see if they are useful.